Okay, let's look at a first example. Let's look at the example of proving that map of g dot f along a list x's is the same as first mapping f along x's and then mapping g along the result. So instead of mapping the composition g dot f, we map the two functions separately. Now I think we can probably see we should expect that to be true, but let's actually write a proper proof by induction that that is indeed the case. So this is what we want to prove, that map g dot f x's is map of g of map f x's. So what do we have to do to prove that by induction? We have first of all to prove that that is true when we replace x's by the empty list. So map of g dot f on the empty list is equal to map of g applied to map f empty list. That's the first thing we have to prove. The second thing we have to prove is that we have that map g dot f on x colon x's is the same as map g applied to map f applied to x's, x colon x's, sorry. And then we assume the result is true on the tail, on x's. So just as we had in defining a function by recursion, in defining the function at x colon x's, we assume we've got the function already defined at x's. Here we're saying in proving something for x colon x's, we assume it's already proved for x's. Right, so that's the shape of what we have to do. Let's get started. So what we have to do here is prove map of g dot f on the empty list is the same as map g applied to map f of the empty list. Well, how can we start? What is map of any function applied to the empty list? It is the empty list by definition of map. So the left-hand side equals the empty list. What about the right-hand side? Well, that's map of G applied to map of F of the empty list, and map of F of the empty list is going to be the empty list. So the whole of the right-hand side equals map G applied to the empty list. And of course, that itself is equal to the empty list. So we've proved that both the left-hand side and the right-hand side are equal to the empty list, so they are both equal. So we've proved what we needed to prove to start the proof off. So we've shown that the left-hand side equals the right-hand side. Okay, that's the first half. The second half, we have to prove map of g dot f applied to x cons x's is equal to map of g applied to map of f applied to x cons x's. And let's do a similar thing of looking at how we can simplify the left-hand side and the right-hand side using the only thing we know is the definition of map and the definition of composition. So what does the left-hand side say? It's map of g dot f applied to x cons x's. Now that, by the definition of map, is g dot f applied to x cons map of g dot f applied to x's. So that's what we have for the left-hand side, and we can simplify that one more step. We know that g dot f applied to x is g applied to f of x. So we've got the left-hand side is equal to g applied to f of x cons map of g dot f on x's. And we can't really go any further. But what about the right-hand side? That is map of g applied to map of f on x cons x's. And that, by the definition of map for f, is equal to map of g applied to f of x cons map f x's. And then by the definition of map for g, we get this is equal to g of f of x applied to map of g applied to map of f x's. So, where are we? We've got two lists, and we know that the elements, the first elements, the heads of those two lists are the same, namely g applied to f of x, but the tails are not. But, we've got our assumption. And that says that map of g dot f applied to x's, we can assume is equal to map g applied to map f x's. And that's precisely what allows us to say that the left-hand side and the right-hand side are equal, because we're assuming that equality between those two versions of maps applied to the list x's. So just as we did with a recursive definition, we define the function on x cons x's using the function on x's. Here we prove the result for x cons x's, assuming that the result is true for x's. And there we have our proof that map of g dot f x's equals map of g applied to f of f x's for all finite lists x's. Because we've shown those two, we showed it outright for the empty list, and we proved it for the list x cons x's, assuming it was true for the list x's. This gives an example, it gives a template for what proofs of properties over finite lists look like. So let's look at some other examples and see where we can go with those.